Imagine a beam of energy so powerful it could erase Earth's protective shield in seconds, or a rogue planet drifting through our galaxy in silence, closer than anyone expected. These are not scenes from science fiction. They are realities reported and studied in 2024 and 2025. All facts in this video reflect discoveries and mission updates from the past 2 years, including insights from the James Webb Space Telescope, Mars missions, new exoplanet detections, and asteroid research. Some of what you'll hear is inspiring, much is unsettling, and it all reshapes how we see the universe and how dangerous travel among the stars may become. Light speed, a deadly energy field. Light speed travel has long been imagined as a shortcut to the stars, but fresh data reminds us why physics resists that dream. At near relativistic velocities, even the sparse hydrogen atoms scattered through interstellar space become a hazard. Each collision at those speeds generates intense secondary radiation and destructive energy, far beyond what a spacecraft or its crew could endure without protection. In that environment, the void is anything but empty. It behaves more like a particle accelerator aimed directly at the ship. This realization has practical consequences for spacecraft design. Engineers now treat shielding not as a supporting feature, but as the critical problem of interstellar travel. Traditional armor, even advanced alloys, would be far too heavy or fragile under constant bombardment. That is why research in 2025 emphasizes concepts still under study, such as electromagnetic barriers or active shielding technologies that might deflect or absorb particles before they release their energy. While none of these approaches offer an immediate solution, the pursuit itself underlines how unforgiving the challenge is. Without a viable defense, relativistic travel would remain not just impractical but effectively lethal. The closer a craft approaches light speed, the more the universe itself turns against it, projecting fields of invisible radiation and destructive force. If the vacuum of space becomes an accelerator at high speed, then only one question remains. What kind of protection could keep a starship intact long enough to reach another world? The answer is far from settled, but while researchers test the limits of shielding, other discoveries from 2025 remind us that danger isn't only found at extreme velocities. Even objects we think of as fixed and familiar carry hidden movement, and those subtle shifts may hold consequences just as profound. The drifting moon. The moon feels like a constant presence above us, yet its bond with Earth is changing in ways that instruments, not human eyes, can detect. Careful measurements confirm that the moon is moving away at about 4 centimeters per year, a shift invisible on human timescales but certain enough over millions of years to reshape our planet's balance. This movement is tracked with remarkable precision. During the Apollo missions, astronauts placed reflectors on the lunar surface. Today, lasers aimed at those reflectors allow scientists to measure the moon's distance down to millimeters. Results reported in 2025 continue to show the same recession, a slow departure unfolding in real time, 1 centimeter at a time. Why it matters comes down to gravity. The connection between Earth and the moon influences much more than tides. It also helps steady the planet's axial tilt and affects the speed of Earth's rotation. As distance grows, that stabilizing grip weakens. Over geological timescales, if this gradual separation continues, Earth's days could lengthen far beyond today's 24 hours, tides could lose strength, and the axial wobble that governs climate stability could become less predictable. It helps to imagine this on a human scale. Billions of years from now, a single day on Earth could last longer than a month does today. The sun might linger high for weeks, followed by nights just as long. Tides that once shaped coastlines and nurtured marine ecosystems could flatten into a gentler rhythm, and the climate's long-term shifts may grow harder to anticipate. Right now, the moon sits about 384,400 kilometers away, the farthest it has ever been in Earth's history. In its youth, it may have hung 10 times closer, filling the ancient skies like a second sun. Since then, every millimeter of distance has accumulated, steadily altering the way Earth and Moon interact. That history continues, written so slowly that no individual will notice, yet relentless enough to leave its mark on the planet's future. What seems unchanging above us reveals its true nature through patient measurement. It is in motion, and that motion tells a story of deep time and ongoing transformation. From the delicate forces sculpting life on Earth to phenomena that bend space and time itself, every discovery reminds us that nothing in the universe stands still for long. Supermassive black holes revealed. In 2019, the world saw the first direct image of a black hole, a hazy orange ring that confirmed what theory had long predicted. Since then, new instruments have sharpened that picture. In 2024 and 2025, the Event Horizon Telescope, using global radio interferometry to link observatories across Earth, produced the clearest images yet of supermassive black holes. At the same time, observations from the James Webb Space Telescope offered fresh perspectives on the dense, brilliant regions that surround these objects. Together, these efforts revealed details that once seemed impossible to observe directly. At the centers of galaxies like M87, astronomers confirmed black holes weighing billions of times more than the Sun. Their event horizons compress this mass into regions only a fraction the size of our solar system. Near those boundaries, gravity bends space sharply enough to distort time itself, while matter funnels inward in enormous disks that flash with heat and radiation. For the first time, inflows around these black holes can be tracked almost as though scientists were watching the frames of a moving picture. The most striking signatures are the colossally long jets of plasma spewed outward. Guided by magnetic fields near the event horizon, matter is accelerated to nearly the speed of light and driven into beams stretching across entire galaxies. Updated imagery now shows these jets rooted to the swirling disks of gas feeding the black holes, confirming how one compact core can influence systems spanning millions of light years. By observing them with this new precision, researchers no longer treat the link between black holes and galaxy evolution as theoretical. It is visible in action. To give the scale some context, imagine placing a black hole like M87's at the center of our solar system. As a thought experiment, nothing would remain stable. The orbits of the planets would collapse or fling outward, leaving no trace of the orderly system we know. It is only an analogy, but it illustrates why the gravity of these objects governs entire galactic neighborhoods. Each new imaging run adds resolution and clarity. Compared to that first blurry ring of 2019, the 2025 datasets make black holes look less like static shadows and more like active machines. With Webb and the Event Horizon Telescope working together, astronomers can now see how matter flows, swirls, ignites, and disappears into darkness with astonishing detail. We can now watch how black holes shape whole galaxies, and that insight is reshaping how astronomers understand both cosmic structure and our place inside it. Yet black holes are not the only forces capable of extreme destruction. Across the universe, there are events that release their energy in a single flash, faster and more violent than anything else known. Cosmic bursts of doom. Gamma-ray bursts, sometimes called GRBs, are among the most destructive forces astronomers have ever studied. In a fraction of a second, they can unleash more energy than the sun will generate in its entire lifetime. They're beams of radiation sweeping outward across the galaxy. They are thought to occur when massive stars collapse into black holes, or when neutron stars collide, compressing unimaginable violence into a single burst of energy. For decades, they were regarded as rare background events, far beyond any realistic danger to Earth. Yet their potential impact is so great that if one aimed directly at our planet, even from thousands of light years away, the results could be devastating. The most immediate concern would be Earth's atmosphere. A gamma ray burst striking at the right angle could strip away much of the ozone layer within moments. With that protective shield gone, intense solar ultraviolet radiation would pour across the surface, damaging DNA and threatening entire ecosystems. Some researchers have even proposed that one of Earth's ancient mass extinctions may have been triggered by such a burst. While direct proof remains uncertain, the possibility underscores how fragile our planet's habitability is when measured against the universe's extremes. Could such an event truly end life as we know it? Scientists warn it could disrupt global systems catastrophically, though complete extinction is unlikely. Until recently, observations of gamma-ray bursts were limited to catching their fading aftermath. By the time telescopes detected them, the event was already over, but monitoring has advanced. As of 2025, satellite networks have linked together with upgraded sensors that can spot bursts almost as they happen, providing alerts within seconds rather than hours. These rapid detections do not prevent the events themselves, but they allow operators and infrastructure managers to prepare for indirect effects, from radiation disturbing satellite electronics to atmospheric changes affecting communication systems. This shift represents a small but important change in perspective. Instead of being completely helpless before the phenomenon, scientists and engineers now study ways to lessen secondary harm. Strategies remain basic: fine-tuning satellites, adapting communication links, and updating orbital procedures. But they reflect an effort to address these bursts not as pure cosmic terror, but as hazards that can at least be partially managed through awareness. Even with closer monitoring, gamma-ray bursts remain unpredictable. Their timing, direction, and strength cannot be forecast, and their destructive potential depends entirely on whether one crosses our path. What improved systems have given us is a faster line of sight, the knowledge that even the most violent events in the universe can be studied in real time. That knowledge reminds us not only of the sheer scale of cosmic forces, but also of how survival depends on the limits of the human body itself, the one factor we carry into space no matter where we go. Zero gravity, human limits. Floating in weightlessness may look effortless, but extended exposure quickly shows the limits of the human body. The experience of astronauts aboard the ISS through 2024 confirmed that microgravity sets off a cascade of changes, and none of them are easy to reverse. Muscles weaken even with strict daily workouts. In zero gravity, there is no natural resistance from standing, walking, or lifting the body's own weight. Fibers shrink, strength fades, and stamina drops. Returning home from long missions often means rebuilding basic mobility, revealing just how quickly the body deteriorates when gravity no longer applies. Bones lose material at an even faster pace. Without the constant loading experienced on Earth, calcium leaches out of skeletal tissue in a process researchers compare to rapid osteoporosis. Density does not always recover fully, even after months back on Earth, raising long-term health concerns. For missions lasting years, such as a round trip to Mars, this poses a serious hurdle to keeping astronauts strong enough to function when they arrive. Fluids drift upward in the absence of normal pressure, pushing against the skull and eyes. As a result, many astronauts report blurred vision or structural changes to eye tissue. These shifts also ripple through the immune system, which shows reduced efficiency under stress. The body adapts, but not always in ways that serve survival. Instead, crucial defenses against illness appear weakened the longer crews remain away from Earth. Radiation adds another layer of strain, saturating tissue with high-energy particles that microgravity does nothing to counteract. Current research aims to develop countermeasures strong enough to protect astronauts from multiple threats at once. The most studied option is artificial gravity, using compact rotating systems to recreate the downward pull. While early tests show promise, no version tested so far has been able to fully halt muscle loss or skeletal decline. These discoveries clarify why human travel beyond low Earth orbit is still carefully constrained. Each weakness compounds the next, creating health risks that medical science does not yet know how to prevent. For those who dream of stepping on Mars, these realities explain why extended missions remain such a high bar. Biology sets limits the timeline cannot ignore. And while human bodies reveal their fragility in open space, the environment itself introduces hazards that seem almost invisible until they cause lasting damage. Even the materials astronauts rely on to build and repair spacecraft can behave in ways unfamiliar to everyday experience. Cold welding, silent space hazard. In space, a simple touch between two pieces of metal can create a problem that looks impossible on Earth. Without air or moisture, there is no protective oxide layer forming on metal surfaces. In a vacuum, atoms at the boundary cannot tell one object from the other. When they press together, they can bond directly, fusing into a single piece without heat or sparks. This effect is called cold welding, and it remains a real maintenance hazard for astronauts. The consequences are more subtle than explosions or dramatic failures, but no less serious. Hinges, fasteners, and connectors that should move freely sometimes lock solid. Records from early satellites and orbital stations describe parts sticking without warning, delaying repairs and trapping hardware in place. Imagine reaching for a tool to loosen a panel bolt, only for the connector to be permanently fused into its housing. No sound marks the event, just an unexpected lock that can stall mission-critical work in silence. Once bound, even small connections can resist any force short of breaking the component entirely. For equipment that must detach or rotate on command, such fusion can cripple entire systems. Engineers account for the risk in spacecraft design, but encounters still take crews by surprise. Each instance highlights how something as ordinary as two metals touching becomes unpredictable in a vacuum. It is an environment where a repair scheduled to last minutes can stretch into hours of improvisation. Efforts to counter cold welding have advanced in recent years. By 2025, surface treatments and nanocoatings are at the center of research, thin protective layers designed to keep atoms from binding across the gap. Initial experiments have shown encouraging results, but they require careful application and may wear down over long missions. Some agencies design around the risk by using composite materials or lubricants that preserve a microscopic barrier between mechanical parts. Yet none of these solutions are foolproof, and the sheer number of new satellites and orbiting modules increases the odds of failure somewhere in the network. Cold welding does not announce itself with sparks or noise. It appears in the quiet failure of moving parts that were never meant to seize. A latch that refuses to open, a joint that locks mid-operation. Each one reminds crews that even minor details carry high stakes. The risk may seem subtle when compared to more obvious dangers, but it belongs to the same category. Forces beyond daily human experience that space makes ordinary. And while cold welding shows how silence in the void can jam vital systems, other hazards arrive with far more visible violence, bringing sudden waves of energy that strike spacecraft and Earth's own atmosphere alike. Solar flares unleashed power. The sun does not emit energy with steady calm. At the peak of its activity, it unleashes sudden bursts of radiation and charged particles known as solar flares. In 2025, the solar cycle entered its maximum phase, a predictable period of heightened turbulence marked by explosive storms driving plasma outward from the solar surface. Though the sunlight we see on Earth appears constant, these eruptions launch invisible electrical storms into space that can cross the distance to Earth in days. When a flare collides with our planet's space environment, the results can become disruptive quickly. Satellites are the first to face the storm head-on. Delicate electronics can short, sensors may be blinded, and entire systems risk permanent loss. Navigation signals, global communications, and weather monitoring depend on technology orbiting just beyond the atmosphere, precisely where solar flares strike hardest. A single severe flare could disable equipment worth billions, cutting off services modern society has come to depend on. On Earth itself, the risks extend to the power grid. When solar energy disturbs the magnetosphere, it sends geomagnetic currents flowing into electrical lines. Transformers, some the size of houses, can overload and fail suddenly under the stress. Historical records show how strong storms once caused widespread outages, from satellite failures to extended blackouts. Engineers have since reinforced grid defenses, but the threat remains present. Loss of GPS positioning, military navigation, aviation signals, or even networked communications could result from a flare strong enough to stir Earth's magnetic shield. Recent measurements in 2025 highlight a rise in X-class flares, the most powerful level observed. These are not automatically destructive, but the increase in frequency has raised the risk profile for grid operators and satellite managers worldwide. Scientists note that peaks of this kind have occurred before, yet the current solar maximum shows unusual intensity. That reminder keeps both researchers and infrastructure planners attentive, knowing the next storm could move from background noise to a headline event without warning. Protective strategies continue to develop. Around-the-clock solar monitoring with both ground observatories and satellite instruments tracks activity across the sun's surface, while artificial intelligence aids in forecasting flare arrival times days ahead. Spacecraft can be powered down into safe modes, and grid managers can reroute or limit loads when warnings arrive early enough. Still, shielding has limits. The magnetosphere absorbs and deflects much of the incoming charge, but it cannot block it entirely. For most of us, the visible reminder comes in the form of auroras, the shimmering curtains of light painted across polar skies when particles from the sun filter downward. Yet behind that beauty remains a more sobering truth. Civilization exists under constant exposure to forces that remind us how fragile its foundations truly are. That fragility extends beyond storms and radiation, into domains where the very structure of space itself may hold risks far more unsettling. Vacuum decay, fragile existence. Physicists sometimes speak of threats that exist only in equations, and one of the more famous is called vacuum decay. This is not an observed event but a speculative idea in particle physics. According to quantum field theory, the vacuum of space itself may not be the final or most stable state. Instead, it could be what scientists call a false vacuum, a temporary energy level that only appears permanent. If space were ever to shift into a lower energy configuration, the change would ripple outward at light speed, rewriting the rules of physics in its path. What makes the idea fascinating, though not frightening, is what it implies. Our reality depends on constants like the strength of atomic forces and the structure of fields that give particles their mass. A transition to a different vacuum state would reshape those constants instantly. Ordinary matter would no longer behave as we know it. Atoms could not bind properly, familiar chemistry would vanish, and even time and space would lose their present meaning. Physicists sometimes describe this as the ground beneath reality being replaced mid-step, not with devastation in the usual sense, but with a complete erasure of the framework in which devastation even makes sense. Despite how unsettling this sounds, present-day science treats vacuum decay purely as a theoretical scenario. Measurements of the Higgs field and related parameters do hint that the universe could occupy such a false vacuum. But if so, the timescales for any possible transition would stretch unimaginably far, longer than the life of stars, galaxies, and perhaps even black holes. In practical terms, it may be an aspect of physics that never manifests at all within the lifespan of the cosmos. The risk is not imminent, nor is it something engineers or agencies prepare for. Instead, it remains a thought experiment that deepens our attempt to understand why the universe is stable at all. The value in considering vacuum decay lies less in the threat itself and more in the questions it highlights. Why is the universe arranged the way it is? And are the laws of physics permanent? These are matters of abstract science, not hazards humanity must guard against. As researchers refine particle physics, they seek not to predict catastrophe, but to explain why existence appears as steady as it does. Speculative physics serves as a reminder that not all dangers are rooted in predictable objects or natural cycles. Some live only in mathematical possibility. Others, by contrast, are tangible, visible, and confirmed. Objects already tracked as they move through near-Earth space, carrying the potential for disasters on scales we can directly imagine. Apophis 2029, Planetary Near Miss. One of the most closely watched celestial events of this decade is already on the calendar. The near-Earth flyby of asteroid Apophis in 2029. When astronomers first charted its orbit in the early 2000s, early models suggested the possibility of a collision, sparking global attention. Measuring more than 300 meters wide, the asteroid was large enough that speculation about its destructive potential, equivalent to thousands of nuclear blasts, captured headlines for years. Refined tracking over the past 2 decades has since eliminated the threat of impact in 2029. By using radar imaging and precise optical observations, scientists have narrowed its orbit to the point where the date is considered safe. Yet safe carries an important qualification. The flyby will bring Apophis extremely close, passing within the region occupied by satellites and well inside the orbit of the Moon. It is a distance considered rare in planetary science, close enough to study directly, but far enough to avoid catastrophe. This closeness transforms Apophis from a potential danger into a natural experiment. As the asteroid swings past Earth, our planet's gravity will bend its orbit. Even subtle changes in speed or angle matter, because they accumulate over decades or centuries. For the first time, researchers can measure this gravitational redirection in real time with a large near-Earth object. The data captured will refine models of how asteroids behave when pulled by planets, a question at the core of understanding orbital mechanics. Beyond the science of trajectories, the encounter represents an ideal training scenario for planetary defense. Methods proposed to divert hazardous asteroids, whether by redirecting them with spacecraft, altering their spin with light pressure, or using gravitational tugs, depend on precision. To change an asteroid's course safely, we must first know how these forces interact with its motion. Observing Apophis in 2029 with telescopes, satellites, and possibly dedicated probes will provide the most detailed test yet of those assumptions. For agencies around the world, Apophis has moved from scare story to case study. Groups tasked with developing asteroid defense strategies already run simulations that incorporate its precise path. Instead of asking what would happen if it struck, they are asking how best to use the event as a model for future interventions. By the time it has passed, the asteroid will have contributed something critical, evidence of how planetary defense theories match reality. Exactly how Earth's gravity tweaks Apophis will teach us how to nudge a dangerous rock in the future. And while that lesson takes place at the scale of one asteroid, other frontiers in 2025 probe something even larger, the earliest structures of the universe itself, seen at distances where time and space push against their own limits. Ancient galaxies beyond limits. The James Webb Space Telescope has delivered findings that continue to unsettle assumptions about the universe's earliest days. In 2024 and 2025, Webb reported galaxies appearing far earlier than standard theory predicted, some dating to only 300 million years after the Big Bang. One press release described them as feeding on streams of cold gas that allowed stars to ignite at unexpected speed. For researchers, that meant galaxies were not creeping into existence slowly, but racing into mature form almost as soon as the universe provided raw material. These systems look surprisingly complete. Instead of faint, fragmentary clusters, Webb's instruments picked out galaxies bright with stars that should have taken far longer to form. The contrast with established models is stark because astronomers long believed gas clouds required countless cycles of collapse and enrichment before real star systems could emerge. If galaxies formed that fast, what does it mean for when the first stars lit up? Webb's data is forcing astronomers to ask that question now. The challenge to theory is clear. Traditional views suggested galaxies assembled gradually over hundreds of millions of years, often through mergers of smaller clumps. But Webb has caught structures that already appear stable and organized at a point when such mergers should not yet have occurred. In response, astrophysicists are reconsidering the physics that shaped the early universe. Some propose that higher density and temperature sped the process. Others suspect changes to our view of dark matter, or even refinements in how inflation unfolded, may be required to align evidence with equations. Each dataset Webb returns carries weight because the telescope is not revealing speculation. It is recording actual light that has traveled across more than 13 billion years of cosmic history. The results compress timelines that, for decades, were taught as settled, rewriting what scientists thought about the dawn of galaxies. Instead of confirming the slow, steady growth outlined by textbooks, the telescope challenges us with evidence of systems rising into existence amid conditions thought too raw and unstable. The broader significance is not just academic. If galaxies could take shape so quickly, then the predictability of cosmic structure itself is in question. It suggests that formation of matter on the grandest scale is more dynamic, less linear, and possibly more chaotic than once believed. Active debate continues about how to interpret these ancient findings. Yet one conclusion is secure. Webb has extended knowledge into a regime that theories alone had not anticipated, and the puzzle of early galaxies is now one of modern astronomy's most urgent frontiers. That urgency carries over into much nearer environments, where recent missions are uncovering mysteries not from the edge of time, but from the surface of a world within reach of our own. Mars breathes strange methane. In recent years, attention has turned from distant galaxies to an atmospheric puzzle much closer at hand. Strange bursts of methane detected on Mars. In 2024 and 2025, the Perseverance rover recorded short, sharp spikes of this gas rising above the planet's surface. Each reading is small compared to Earth's emissions, yet on Mars, where the atmosphere is thin and methane should quickly break down under ultraviolet light, their persistence is difficult to explain. Instead of fading entirely, the gas seems to return in irregular pulses, as if the planet exhales from hidden reservoirs below. Two main explanations guide the debate. The first points to geology. Methane might form underground when water interacts with certain minerals, seeping slowly to the surface through fractures in the crust. Evidence for this kind of chemical process exists in Mars' rock record, though no single sample has tied methane emissions to a direct source. The second possibility is more provocative, though still speculative. On Earth, methane is also created as a byproduct of life, mostly by microbes. If organisms once existed on Mars, or if some endure beneath the surface, their waste gases could explain the measured spikes. For now, neither hypothesis is confirmed. The irregular nature of the bursts deepens the mystery. Readings sometimes cluster near specific craters and then vanish for weeks, raising questions about whether they result from local geology or something more dynamic happening below. Day-to-day variations make it difficult to separate signal from noise, and scientists caution that atmospheric effects might also distort the data. Yet every new detection builds a record of where and when methane occurs, making future comparisons more powerful. By tracing patterns across seasons and locations, researchers hope to narrow the options. For scientists, the presence of methane alone makes Mars more intriguing than before. Whether caused by geology or biology, the discovery proves the planet is not chemically static. Something beneath the surface is active enough to release gas into the open sky, an outcome that challenges the old picture of Mars as a silent, frozen desert. The fact that such activity continues today suggests an inner planet still in motion, still capable of surprises. Perseverance keeps sampling the air and soil, compiling a dataset that will take years to unravel. Each whiff of methane is a clue, and each clue sharpens the outline of the riddle Mars presents. The planet is unsettled, and the question of what truly drives that behavior remains open. Perseverance keeps sniffing. Each new reading narrows the mystery. And that mystery feeds into a greater question shared across astronomy. If life or preconditions for life can hide beneath such harsh conditions, then how might it exist in even stranger worlds, where no sunrise ever breaks the horizon? Rogue planets, worlds without suns. Not every planet has a star to call home. Some worlds drift freely through the galaxy, unbound, moving in silence along paths that never return to a central sun. These are known as rogue planets. Cast out of their original systems, they wander in permanent darkness, hidden against the backdrop of space and imperceptible without specialized instruments. By 2025, evidence from microlensing surveys has strengthened the idea that the Milky Way may contain very many free-floating planets. Some are believed to tower in size like Jupiter or Saturn, while others may resemble Earth in scale and rocky composition. What unites them is their isolation, journeys made without the steady heat and light of a nearby star. Their sheer numbers suggest planetary formation might be far more common and far messier than once thought. Conditions on such worlds seem hostile at first glance. With no sunlight to warm their surfaces, these planets plunge into deep cold, their exteriors hovering near absolute zero. Yet a planet is not defined solely by its surface. Beneath thick shells of ice, internal heating, driven by radioactive decay or a molten core insulated from the vacuum around it, might sustain subsurface oceans. On Earth's moons like Europa and Enceladus, similar processes maintain liquid water beneath ice, offering clues to how a rogue planet could remain active below its crust. Some models extend this possibility further. A rogue planet surrounded by a dense atmosphere rich in hydrogen could trap internal heat, creating stable layers of warmth despite external cold. In such conditions, chemistry might proceed in ways that make habitability at least possible. If life were ever to emerge there, it would live not by sunlight, but by chemical energy drawn from rock, water, and internal heat. Researchers stress this remains speculation, but the physics that could sustain it are real. Detecting rogue planets remains a challenge. Unlike stars or orbiting planets that emit or reflect light, these bodies are almost invisible. Most discoveries come through gravitational microlensing, when a rogue planet briefly bends the light of a distant star as it passes between us and that background glow. Each rare detection hints at thousands more moving unseen, scattered across the galaxy. If even a fraction host warm interiors beneath their frozen shells, the potential habitats for life extend far beyond what astronomers once imagined. A frozen world drifting alone could still hide an ocean, and maybe life, held alive by radioactive warmth under an icy crust. While such discoveries expand the boundaries of habitability closer to home, a very different challenge is already underway: preserving the narrow band of space around Earth itself from a hazard entirely of our own making. Space junk crisis. Orbit around Earth is no longer an untouched frontier. After decades of launches, discarded rocket stages, and fragments from aging satellites, near-Earth space has filled with debris. By 2025, tens of thousands of objects are tracked closely enough for collision monitoring. Each piece, no matter how small, travels at speeds exceeding 25,000 kilometers per hour. At that velocity, even a stray bolt carries the destructive force to puncture or tear apart a spacecraft, spreading countless new fragments into orbit. This escalating chain reaction is known as the Kessler syndrome. Once treated as a remote scenario, it is now a growing possibility. Every impact creates more fragments, and those fragments in turn threaten additional collisions. Over time, the process can multiply exponentially, leaving low Earth orbit filled with clouds of shrapnel. Even without new launches, the existing debris is enough to fuel self-sustaining risks. What once seemed like an abstract concern has become a pressing challenge for every nation and company operating in space. The consequences reach far beyond orbital mechanics. Satellites manage weather forecasting, global communication, navigation, scientific monitoring, and even defense infrastructure. A single destroyed satellite can disrupt services on which millions of people rely, from airplane routing to financial networks. Operators today perform regular adjustments to dodge tracked debris, but every maneuver consumes onboard fuel and shortens the satellite's life. With private industries expanding massive constellations, the pressure on limited orbital lanes increases steadily. As a result, cleanup proposals once dismissed as science fiction have advanced into trial programs. Concepts range from electromagnetic tethers able to drag inactive satellites into the atmosphere to self-targeting nets or robotic arms capable of capturing defunct equipment. Ground-based lasers are also under experiment, designed to gently nudge smaller fragments so they lose altitude and eventually burn up. While no single approach yet works at scale, agencies are investing in rapid research with the hope of preventing long-term orbital congestion. Despite these efforts, mitigation continues to lag behind the pace of debris creation. Each fresh launch adds more potential fragments, while uncontrolled collisions multiply hazards faster than cleanup measures can compensate. The threat does not depend on a catastrophic impact with a crewed mission. It only takes one shard piercing a commercial satellite to cause huge economic losses and disrupt services felt directly on Earth. If unchecked, low Earth orbit could become increasingly dangerous, limiting exploration opportunities and obstructing the very systems modern life depends on. This danger highlights how fragile our infrastructure can be, even at the edge of space. But while Earth's orbit illustrates the cumulative risks of human activity, elsewhere in the cosmos, there are forces of destruction driven not by us, but by the universe itself, collisions so violent they reshape matter at its most fundamental level. Violent neutron star collisions. Neutron stars are among the strangest remnants left behind after massive stars collapse. Imagine compressing more mass than our Sun into a sphere no wider than a large city. Inside, matter exists in forms unknown on Earth. Electrons are forced into protons, leaving nearly pure neutrons packed so tightly that a single teaspoon of the material could weigh billions of tons. These compact objects circle one another in silent orbits, their mutual gravity slowly draining orbital energy. Over time, that spiral pulls them closer until, inevitably, they collide. When two neutron stars crash together, the results reach far beyond light and heat. The immense force shakes the very fabric of space, creating gravitational waves that ripple outward at light speed. Sensitive detectors like LIGO and Virgo, operating into 2024, have now recorded many of these spacetime vibrations, confirming that such collisions are not rare on cosmic timescales. Simultaneously, telescopes scanning the sky pick up the flare of visible light released when matter is thrown outward. The combination of gravitational wave data with optical signals marks one of the clearest examples of multi-messenger astronomy, different instruments capturing different aspects of the same event. The light signature of these collisions is called a kilonova, a brief, intense flash as neutron-rich debris blasts into space. While the flare fades quickly, it highlights a deeper significance. The extreme environment created in the aftermath is where many of the universe's heaviest elements are made. Gold, platinum, uranium, and other heavy materials impossible to form in ordinary stellar fusion are forged here in staggering quantities. Astrophysicists now treat these collisions as the major source of such elements, solving a question that puzzled science for decades. It means that much of Earth's inventory of rare metals traces back to catastrophic impacts of stars that ended their lives long before our solar system formed. Observing these events has changed the practice of astronomy itself. For centuries, nearly all knowledge of the cosmos came from light, collected through telescopes in every wavelength. Now, gravitational waves add a second channel, allowing researchers to not only see but also listen to the universe. Each recorded event enriches that library, sharpening models of how matter behaves under unimaginable density and confirming Einstein's predictions about the nature of gravity. Taken together, they show that even the most violent acts of destruction are also acts of creation, dispersing ingredients that eventually seeded worlds like ours. Some of the gold in your jewelry was forged in the smash-up of dead stars. And while those collisions connect directly to what we see and use on Earth, newer discoveries focus on worlds far beyond, planets whose skies can now be read as clearly as the materials left behind by ancient explosions. Exoplanet atmospheres revealed. For decades, exoplanets were little more than shadows against their stars, detected by slight dips in starlight or subtle wobbles in stellar motion. Today, that picture looks very different. By 2025, the James Webb Space Telescope has turned these dots of light into objects whose skies can be studied directly. When a planet passes in front of its star, some starlight filters through its atmosphere, and Webb's instruments split that light into spectra, patterns that reveal the gases shaping those alien worlds. This technique has already yielded discoveries once considered out of reach. JWST has detected molecules like water vapor, carbon dioxide, and methane on multiple planets, and even hints of more complex chemistry on worlds such as K218b and 55 Cancri, E. These findings do not prove that such places are habitable, but they show atmospheres rich enough to demand closer study. For the first time, scientists can state with evidence that certain exoplanets carry chemical ingredients important for climate, energy balance, and possibly processes resembling those that shaped early Earth. Where these planets orbit matters just as much as what fills their skies. A number of them lie within a star's habitable zone, the orbital range where liquid water could exist at the surface. Webb's data has shown that some of these candidates not only occupy this region, but also appear to have atmospheres thick enough to regulate temperature. That makes them more than inert rocks circling at the right distance. It makes them places where weather, oceans, and surface cycles might actually occur. One of the clearest examples is K218b, larger than Earth, yet smaller than Neptune. It revealed an atmosphere with hydrogen and potential organic molecules, a chemistry more diverse than astronomers expected. Instead of conforming to neat categories like rocky or gaseous, planets like this present entirely new kinds of worlds. At the same time, hot, close-in planets such as 55 Cancri E have produced evidence of exotic compositions, pointing to atmospheres shaped by blazing, unstable environments. These examples reveal the diversity now accessible, where each planet feels less hypothetical and more like a specific, measurable environment. Perhaps most strikingly, Webb has detected patterns that suggest cloud layers drifting across alien skies. Variations in spectral signals point to changing cover, hinting at winds, weather fronts, and possibly even seasonal cycles on worlds many light-years away. In effect, we are now beginning to chart climates outside our solar system. These are not just lists of numbers, but evidence of genuine weather taking place on worlds entirely unlike our own. We can now check alien weather. How wildly different could a single day feel on another planet? The answers are beginning to emerge, and they remind us that as powerful as instruments have become, some of the greatest forces in the universe remain beyond our sight, shaping the cosmos without light at all. Dark matter's map emerges. Dark matter remains one of the most perplexing subjects in modern science. It does not shine, it does not reflect, and no telescope has captured it directly. Yet its influence is unmistakable. The way galaxies rotate, the way clusters of stars stay bound, and the way light bends around unseen structures all point to mass that ordinary matter cannot supply. Something hidden adds this extra gravity, and scientists call that invisible source dark matter. By 2025, astronomers created the most detailed maps yet of this unseen framework. They relied on gravitational lensing, a phenomenon where massive objects warp and distort light coming from galaxies far behind them. By tracking these distortions across large regions of the sky, researchers traced where the invisible mass must be located. Piece by piece, these measurements revealed the outlines of structures that extend far beyond individual galaxies, forming a network that gives the universe its underlying skeleton. What emerges looks like a vast web. Filaments of unseen matter stretch for billions of light years, connecting nodes where galaxy clusters sit like knots in a cosmic net. At those intersections, dark matter's gravity anchors not just stars and gas, but entire galactic families. Without it, spiral galaxies would spin apart under their own speed, their visible matter incapable of holding together. The maps confirm theories first proposed decades ago. Dark matter acts as a kind of gravitational glue, a hidden framework upon which the luminous universe has been assembled. Still, these advances chart shapes, not identities. Despite decades of effort, no experiment has captured a dark matter particle or confirmed what it actually is. Physics offers candidates, weakly interacting particles, axions, or entirely new forms of matter, but none have been demonstrated in a lab. Each failed attempt leaves the mystery unresolved, even as cosmic maps grow ever more precise. Our instruments can trace the shadow of dark matter on light, yet the substance itself continues to elude direct evidence. For now, astronomers move forward by following the ghostly imprints it leaves. Every warped image of a distant galaxy is another data point on where this concealed mass must lie. With each refinement, the paradox intensifies. The universe's scaffolding becomes clearer, while the nature of the material holding it together retreats further from our grasp. We can now see dark matter's shape across the cosmos, but not its substance. And while such mysteries stretch across unimaginable distances, closer to home lies another force shaping daily survival: the cycles of energy from our own star, whose eruptions mark one of the most immediate threats to technology and life on Earth. Solar maximum, peak storm cycle. The cycles of the sun reach a natural high point about every 11 years, and 2025 marks one of those crests. This phase, known as solar maximum, brings a surge in magnetic storms, flares, and surface activity that ripple into space. It is beautiful high-latitude auroras for us, its stress tests for infrastructure. For about 2 years, the sun operates in this restless state, its surface crowded with dark sunspots and eruptive events that remind scientists and engineers why close monitoring never stops. The most immediate adjustments come in how systems on Earth respond to the constant volatility overhead. Airlines at high latitudes reroute flights away from polar regions, where cosmic and solar radiation intensifies during storms. This operational change helps protect passengers and crew while avoiding communication blackouts that can occur near the magnetic poles. Grid operators, meanwhile, brace for geomagnetically induced currents flowing into transmission lines. These invisible surges, linked directly to solar storms, can overload transformers originally built to withstand only normal demand. Protective shutdowns and rerouting of power are now standard precautions at peak solar activity. Observation methods have improved as well. Continuous solar monitoring stations, both ground and space-based, track sunspots and flare activity with finer detail than ever before. Prediction systems powered by AI models now give operators hours of advanced warning for incoming disturbances. These alerts do not remove the hazard, but they allow satellites, airlines, and grids to activate protective steps before the storm arrives, reducing the risk of cascade failures. In effect, civil infrastructure is learning to anticipate the sun's moods, just as weather services anticipate terrestrial storms. Of course, solar maximum brings more than systemic risks. Across the skies, bursts of charged particles colliding with Earth's magnetic field create luminous auroras far beyond their usual zones. Curtains of green, purple, or red light drift over latitudes unaccustomed to such displays, replacing routine skies with striking reminders of solar power. These temporary expansions of auroral ovals often reach locations that have no history of such phenomena, offering glimpses of space, whether that both inspire and warn at once. For science, these events hold value beyond spectacle. Each flare and storm builds a record that teaches how Earth's systems respond under extreme pressure. As solar maximum peaks, the data gathered will frame how future missions, technologies, and defenses align against natural forces far beyond human control. And while this current cycle centers on how a star shapes life and systems on Earth, elsewhere in the solar system, another set of environments is stirring attention. Worlds where invisible oceans may be hiding secrets far more profound. Oceans on hidden moons. Among the most intriguing places in the solar system are two icy moons, Europa orbiting Jupiter and Enceladus circling Saturn. Both carry convincing evidence that beneath their frozen crusts lie vast oceans of liquid water. These oceans are not just speculation. By 2025, multiple observations confirmed they remain active and dynamic, sustained by tidal flexing from their parent planets, immense gravity. The discovery does not portray dead worlds locked in ice, but rather environments where internal energy continues to shape water-filled interiors. Enceladus demonstrates this activity in a striking way. Its south polar surface is cut by long fractures that act as vents, spraying towering plumes of vapor into surrounding space. Spacecraft instruments passing through those plumes measured salts, organic molecules, and ice grains, each pointing to contact with a salty subsurface ocean. That these geysers continue erupting, powered by Saturn's pull stretching the moon's interior like a bellows, proves the ocean beneath is no relic. For such a small body, only a few hundred kilometers across, the strength of its ongoing activity has made Enceladus one of the highest value targets for astrobiology. Europa reveals itself more subtly. Its surface fractures into shifting networks of ridges and cracks, a surface pattern that echoes deep forces below. These marks are believed to result from tidal heating caused by Jupiter's gravitational pull, flexing Europa's core, and preventing its immense ocean from freezing solid. Measurements of slight shifts in the moon's outer shell, recorded in 2025, reinforced the view that water is churning beneath kilometers of ice. Taken together, the evidence suggests Europa may hold more liquid water than Earth, locked away in a protective shell that keeps the ocean stable over geologic timescales. The significance of these hidden seas lies in what they might harbor. On Earth, deep-sea hydrothermal vents support entire ecosystems using chemical energy rather than sunlight. There, microbes and larger organisms thrive in complete darkness, feeding on minerals vented from the ocean floor. A similar process could arise on Europa or Enceladus, where hydrothermal activity at the rocky core may deliver energy and nutrients directly into the water column. Protected under kilometers of ice from radiation, such locations could provide some of the most favorable conditions for life beyond Earth. Upcoming mission studies reflect this potential. Probes and landers are already in the planning stages, designed to either fly through plumes or sample surface ice for signs of chemical imbalances or complex organics. These techniques could offer strong evidence of biology without needing to drill directly into the oceans themselves. If we find life there, it would be life independent of sunlight, an enormous discovery that would redefine how and where biology can exist. Insights from these hidden oceans are reshaping what we imagine the universe could host. But while these environments may lie far from Earth, another challenge is unfolding much closer. One not born of nature at all, but created by our own technology filling the skies. Starlink in the sky. Across the night sky, a new kind of constellation has emerged, not of stars, but of satellites. Among these networks, none is more visible than Starlink, which by 2025 has grown into a massive array of thousands of units steadily circling Earth. To the naked eye, they appear as faint moving points at dusk or dawn. For astronomers, though, their presence is harder to overlook. Trails of reflected light routinely cut through images where uninterrupted darkness once revealed galaxies and nebulae. For observatories that depend on long exposures, the problem cuts especially deep. Capturing signals from some of the faintest and most distant objects requires hours of uninterrupted observation. Yet each exposure now risks contamination by streaks of reflected sunlight. Where early satellites presented occasional interference, constellations numbering in the thousands create a density of trails that overwhelms certain kinds of research. A streak across a single exposure may sound trivial, but when multiplied across survey projects that seek out faint galaxies or undiscovered asteroids, the effect becomes an irreplaceable loss of data. Astronomers describe these intrusions as scars through their observations, erasing details that cannot be recovered. Projects mapping ancient galactic structures or monitoring near-Earth objects often find frames rendered unusable. Particularly frustrating is that the issue is not spread evenly. Certain regions of the sky and specific times of night are hit far harder due to satellite positioning. For global survey programs working to measure light nearly at the limit of detection, thousands of artificial trails introduced in a single session can undermine years of planning and investment. Satellite operators have acknowledged the issue and tested partial fixes. Some spacecraft are now coated with darker materials to reflect less sunlight back toward Earth, while others tilt during key hours to minimize brightness. These adjustments have reduced glare by some measure, but not enough to bring conditions anywhere close to past clarity. At a scale of thousands, even slight reflections accumulate into significant obstacles for professional astronomy. For researchers, the night sky increasingly resembles a canvas overlaid with moving signatures humanity has created. The situation has created a cultural and scientific tension. On one side, constellations like Starlink promise global internet access, offering underserved regions a connection that traditional infrastructure cannot easily supply. On the other, an ever-brightening sky risks diluting one of the oldest shared inheritances, the ability to study and wonder at the universe unobstructed. The question is no longer about whether satellite constellations provide value. They clearly do. But whether that value outweighs the scientific cost of transforming the heavens into crowded corridors of light. Is global connectivity worth changing our night sky permanently? Share what you think in the comments below. Because just as satellites alter our view, other signals, faint and ancient, still echo all around us, carrying evidence from a time when the universe itself was only beginning to shine. The universe's faint afterglow. Among the most enduring clues to the universe's beginnings is a faint glow stretched thin across the sky, the cosmic microwave background. This ancient radiation marks the moment when the hot plasma of the early cosmos cooled enough for atoms to form, allowing light to travel freely for the first time. What we detect today is not bright starlight, but a low-energy whisper imprinted more than 13 billion years ago, a 8 billion year old footprint that still surprises us. Astronomers describe it as a kind of photograph from infancy, preserving subtle traces of how space itself first settled into order. In recent years, new measurements sharpened this cosmic image in ways that puzzled researchers. Precision studies leading into 2024 and 2025 revealed alignments in the background's faint ripples, shapes and patterns that standard models did not anticipate. Normally, The microwave background should display near-uniform randomness, with slight variations seeding galaxies that would grow later. Yet the unexpected signals, sometimes called anomalies, have encouraged scientists to test whether parts of our current framework, such as the details of cosmic inflation, might need refinement. These findings do not dethrone the theory, but suggest it may not tell the entire story, leaving open questions about what really happened in the universe's earliest fractions of a second. The significance lies in what those ripples represent. They are fossil records of tiny density shifts that later became galaxies, clusters, and the large-scale web of matter stretching throughout the cosmos. If early conditions carried hidden symmetries, or if the expansion of the universe left behind faint imprints unaccounted for, then each anomaly is a clue to physics beyond our present reach. Researchers emphasize caution, since such alignments could one day prove to be statistical quirks rather than signs of deeper laws. Yet even with decades of analysis, no explanation has erased the mystery outright. At the edge of observation, the background reminds us that reality's foundations might still hide undiscovered rules. The cosmic microwave background is powerful not because it answers everything, but because it still leaves much unresolved. It teaches us that even after half a century of measurement, the universe's afterglow holds quiet contradictions in its structure. That tension keeps scientists listening carefully, balancing the known against the unknown, as if the faint glow itself were still whispering unfinished instructions from the dawn of time. From these ancient imprints on the fabric of space, attention shifts to something far closer and more tangible, objects arriving within our own solar system that bear no connection to the Sun and no history tied to Earth, yet carry their own stories across the stars. Visitors from beyond. The first time astronomers realized an object from interstellar space had entered our neighborhood was in 2017. Named Oumuamua, it sped past the Sun on a hyperbolic trajectory that proved it did not belong to our system. Its velocity was too great for the Sun's gravity to hold, meaning it came from far beyond and would never return. Just 2 years later, a second visitor appeared, Comet 2I/Borisov. Unlike the strange shape of Oumuamua, which defied easy classification, Borisov looked more like the comets we know, bright with a glowing tail. Yet its chemical makeup revealed an origin in another star system. Those discoveries marked the beginning of a new era, one showing that interstellar wanderers are not rare flukes but steady travelers crossing our skies. By 2025, surveys and monitoring programs are confirming this pattern. With upgraded sky mapping systems constantly scanning the heavens, astronomers have begun flagging candidates far more frequently. And in one case, the James Webb Space Telescope played a direct role, observing the interstellar comet 3I Atlas in remarkable detail. These observations give scientists their first opportunity to compare chemical signatures between comets from our own neighborhood and those born around other stars. The result is more than curiosity. It provides physical samples of the galactic environment delivered into reach, brief reminders that our solar system moves through a wider stream of interstellar debris. Each discovery raises new questions. The brightness variations of Oumuamua suggested an unusual, elongated body, unlike common asteroids. Some interstellar candidates even show accelerations that appear slightly beyond those predicted by gravity and outgassing alone. That uncertainty pushes against standard categories and hints at different formation processes in distant planetary nurseries. No single explanation fits easily, leaving the door open to possibilities ranging from unusual ices to the effects of radiation heating in environments unlike our own. For scientists, however, the real value lies in what these bodies carry. Every spectrum taken from an interstellar comet is, in essence, a record of chemistry shaped in another system. Molecules embedded in their solids and gases trace the environments of alien protoplanetary disks, offering glimpses into how other stars assemble planets. Each visitor is a free sample from somewhere else, drifting through our reach only for short windows before vanishing again into the dark between the stars. The challenge is time. These objects move quickly, and the openings for study are measured in weeks or months before they fade from view. Very few will ever be close enough for spacecraft encounters, so astronomers treat spectral snapshots as the next best thing. Still, even from a distance, such fragments hint at the diversity of planetary systems and at conditions that may resemble or completely differ from those that foster life. Each visitor is a free sample from another system. What secrets could it carry? And as scientists pursue those secrets, another effort closer to home is underway, deciphering how to anticipate powerful forces from our own star in order to protect the systems we already depend on. Predicting space weather. By 2025, watching the sun has become as critical as watching the weather. What was once an unpredictable hazard is now a field managed with networks of satellites and ground stations feeding constant readings into advanced models. Instead of waiting for storms to appear without warning, scientists now work with data streams that map solar activity in real time and project when bursts of energy are likely to reach Earth. For the first time, space weather is tracked as continuously as the atmosphere above our heads. The speed of interpretation has changed dramatically as well. Artificial intelligence systems now parse enormous amounts of solar data, measuring shifts in magnetic fields, tracing the growth of new sunspots, and calculating the probability of eruptions, at a pace far faster than human analysts alone. This acceleration moves the warning window from a few hours to days in advance, giving industries the crucial time needed to act. The difference is practical. What once left systems vulnerable now gives operators a chance to prepare. Those warnings matter most where technology meets risk. For satellites orbiting Earth, an early alert can trigger protective steps. Sensitive instruments can be powered down, antennas shifted into safe configurations, and operations paused until the threat passes. Similar strategies extend to power grids on the ground, where protective modes divert or release excess load before geomagnetic surges can damage transformers. Airlines, particularly those flying polar routes, use forecasts to replan courses in advance, reducing exposure to both heightened radiation and communication blackouts at high latitudes. Communication networks, too, benefit directly. Signals that would normally degrade or vanish under solar interference can be rerouted through alternate satellites or timing, adjusted to avoid peak disturbances. The advantage lies not in eliminating disruption, but in reducing its reach. These layers of protection mean that storms capable of major outages a decade ago now pass with minimal interruption, a result of preparedness rather than diminished solar power. Still, the limits of forecasting remain clear. No system can prevent a massive flare, only anticipate it. Over-reliance on models carries risks of false alarms or underestimated events, and the complexity of plasma storms ensures surprises remain a certainty. The solar maximum of 2025 continues to press these systems to their limits, testing whether today's models can hold against tomorrow's storms. Each correct prediction builds confidence, but each miss highlights how fragile our dependence on accurate forecasting truly is. For now, prediction represents a rare kind of protection, quiet, technical, and underappreciated, yet vital for safeguarding everything from airplanes overhead to the power running through every city. It reminds us that even as science learns to anticipate danger, the universe itself does not pause. Its cycles continue to unfold, carrying new wonders and hazards in equal measure. The discoveries of 2025 reveal a universe that is both beautiful and hazardous, filled with forces that inspire wonder while also reminding us of their potential to disrupt life and technology. From rogue planets to black holes, and even speculative physics like vacuum decay, each finding shows how fragile our picture of existence can be, even if most risks remain extremely unlikely. Our task is not only to observe but to prepare, building observatories, improving warnings, and protecting the systems that let us explore further. Subscribe for more updates and share in the comments which 2025 discovery surprised you most and why.